On the bottom, conclusion on nonlinearity and the consequences for the two equations. So for people who don't know the two presenters, Miguel Onorato is full professor for the Department of Physics, University of Turin. And Sergei Annenkov is a teaching fellow in mathematics and data science of the School of Computing and Mathematics at Keele University in UK. So the two presenters have 20 minutes, more or less, one more minute if they want, and then to leave 5 to 10 minutes for the discussion. So Miguel, if you want, you can start.
Okay, so let me share my screen. Okay. Okay, do you see my full screen?
Perfect.
Perfect. So let me start. So good afternoon to everyone, and or I don't know, good morning maybe if you are the other side of the ocean. So some thanks first of all, Elvise, and all the organizers for giving me the opportunity to share my research activity. And so this talk will be on the wave kinetic equation, which include dissipation. This is a result that we have obtained in collaboration with Giovanni De Matteis, who was a student at the University of Torino. Now he's in Rensselaer Polytechnic Institute in New York. Davide Maestrini, who is a postdoc in my department, and Daniele Noto, who was a master's student when he started doing the calculation. And now he's doing a PhD in Sorbonne University in France. And I also would like to acknowledge Sergei Nazarenko, Jalal Shatta, and Yuril Vod for discussion. So really, I'm happy to give a talk in this environment, in the WISE community, since that's the place where I started basically working on waves. So I've been participating to the WISE meeting for many, many years. And then, well, the last one was in Venice in 2016. Now, due to some changes in my research activity, I'm doing something else, but still I am very much interested in water waves. And this is what the outcome of what we have done recently. So let me give you some motivation. I have seen, I mean, the audience, I've seen many people who are very experienced. Maybe it's going to be a little bit boring this part, but let me introduce this, the wave action balance equation, which is written there. It's a single point in the sense that I assume homogeneity, okay? And you see on the right-hand side, you have what people call source terms, okay? Well, actually, SNL is not a source term, but they call it source term, so I adapt myself to that. So then we have a dissipation term and an input term, which is given by the wind. So this is the base of the wave forecasting models. And so we're working in a two-dimensional field, okay? And so K is a vector. It's not bold, it doesn't have an arrow, but it's in R2, so it means that we are on a surface working, okay? And I mean, this SNL is the result of work that has been done originally by Nobel Prize Klaus Hasselmann and by Vladimir Zakhadov, the Dirac medalist. And I mean, the important thing about this collision integral, which comes directly from the equation of motion, is that the collision integral contains, I mean, it's responsible for the transfer of energy between modes, and it contains two delta functions, two Dirac delta functions, one over wave number and the other over frequencies. And so this term is just different from zero only if exact resonant conditions are satisfied, okay? Then we have the other two, the source term. I know that in the wave forecasting community, everything is much more complicated than that. So I really simplify things and I try to stay at the fundamental level. So we have a dissipation. Usually dissipation is given in a form in which you have gamma of k, which is some function which comes originally from work of Hasselmann on white capping, and is proportional to SS is proportional to NK. And the input term is the wind. Originally, it comes from wind, so originally again from maths, but then I'm sure there have been many development, and many of you in the audience know much more than I do in this on this term and on these source terms. Okay, so this is basically the base of our forecasting models. But the statement, I think the important statement that I would like to make now is that the present formulation of this wave action balance equation implies a separation of scales. Okay, so basically, if you want to see things in terms of, let's say, wave turbulence theory, you have to assume, for example, that you have some forcing at low wave numbers, you have some damping at some dissipation at high wave numbers, and then you have some sort of inertial range or region of transparency in which non-linearity act, and they transfer energy from one mode to the other. So, this means that those terms should have either on different scales or on different time scales, in the sense that you may have also dissipation at the scale of where nonlinearity acts, but it should be should act on a longer time scale. So this is the hidden hypothesis, which are under one of. There are many hypotheses under this equation, but this is one important, and this is what I would like to discuss. So this is the first motivation, this separation of scale that I would like to talk about. And then I have also another motivation, which is the following. Okay, during the past year, there has been many interesting work trying to reproduce the omega to the -4 spectra that we usually observe in field experiments, right? If you do a field experiment, you measure time series, you compute spectrum, you usually see a omega to the -4 range, and then power law, and then maybe goes to -5 and so on. But this -4 is also an exact solution of the wave kinetic equation, so it has some relevance. However, when people have tried to reproduce this omega to the -4 spectrum in wave tank experiments, the results have been quite unsuccessful. And here in this plot, what I show is the exponent of the spectrum. Each dot is an experiment that has been performed in a different wave tank. Okay, and so each dot is a slope that has been performed for a specific wave stiffness. And omega to the -4 is this dashed line here. And you can see that many experiments, and the experiments are done in the following way. We usually, one pumps energy at some low frequency and expect to have a formation of a spectrum, so a direct cascade, and formation of a power law. But the exponent is not always omega to the -4, but you have, a range of exponents which are much lower than that. There could be many causes of this, so finite size effects, maybe, but also has been pointed out that, for example, by Mordan, that dissipation could be also, when you are at small scales, dissipation may also play an important role. And maybe when dissipation is on the same time scale as the nonlinearity, maybe something important can take place. Okay, so those are somehow some motivation that I've been thinking about for the past years, and there are some open questions which I think are relevant, and are relevant not only if you are thinking about experiments in a wave tank facility, but also maybe in general for conditions in open ocean. So. And those are the open questions that I am thinking. I'm not going to give an answer to all these things, but just to drive you through my presentation. So, what does happen if nonlinearity and dissipation act on the same time scale? So, this is the first question, and is related to that: is the wave action balance equation modified? And if yes, what is the role of exact resonances in this case? So, if you have an exact resonance, if you have dissipation on the same time scale, do resonances play an important role, or not? So what we have done, we have made recently, we have made an attempt to derive a wave kinetic equation starting from Zakharov equation, but including dissipation at the deterministic level. Okay, so this is what we have done, and here is first let's say result, but this is somehow trivial. But let's now suppose okay that dissipation is acting on a slower time scale than nonlinearity. Okay, so nonlinearity is faster than dissipation. So so this is what we start with is the Zakharov equation, and I hope most of you are familiar with the Zakharov equation. If not, this is just a variable ak, which is related to the surface elevation. We're working in Fourier space. I am assuming periodic boundary conditions. So we have discrete modes, and these are sums. This is just the linear part. So omega is dispersion relation. This is a coupling coefficient T, and this is Kronecker delta, which allows for wave interactions. Here I put an epsilon in front of the nonlinear term in order to ensure that, I mean, we have the nonlinear linear part order 1, and then we have epsilon, the nonlinearity. And then what we can do, we can put a dissipative term, okay, on the right-hand side, which is here. This is, I mean, I'm not prescribing the shape of gamma of k, okay? I'm not prescribing this, but it's just a general approach. So I'm saying that just that there is a dissipative term, which is on a time scale which is lower than the nonlinearity. So it's the time scale of this term is 1 over epsilon square, okay? So gamma is the damping coefficient or dissipation coefficient. Okay, then we do all the math, okay? And you look for an equation for AK modulus square. You can use different way of doing that, but at the end of the story, the result that you get is this one, okay? So this is the one that you get, so which is quite normal in the sense that this is what you get at the standard kinetic equation, so the start and collision integral, and an extra term which account for dissipation. And this is basically what, I mean, what is in the wave modeling in the energy balance equation that is solved for wave forecasting, okay? So this is, I mean, if dissipation acts on a larger time scale, everything is fine. Just, I mean, just from going from the discrete model to the continuous model, you have to take the large box limit. L is the scale of the box size, and you take the large box limit and you define nk in this way. So you go from sums to integral. Okay, so far so good, at least to me. But now what happens if nonlinearity and dissipation are acting on the same time scale? Okay, so that's the next question. So you see here again, we have Zakharov equation, nonlinearity order epsilon, but now the damping is order epsilon as well. So the nonlinearity is on the same time scale as the dissipation here. And what we do then, I mean, I'm giving you just the final result, and maybe if I don't know if I have time, I will sketch just and I will give you an outline of the derivation. But the final result that we get is the following. So you get this equation, okay, which the collision integral will resemble very much the standard collision integral, which is here. But instead of having 1 over n1, 1 over n2, 1 over n3, and 1 over n4, you have this coefficient ak, which is given by delta omega. Well, this delta omega is omega 1 plus omega 2 minus omega 3 minus omega 4. Okay, so it's delta omega squared divided by delta omega squared plus gk squared, and this gk squared is a term which is related to the damping, so it contains the dissipation gamma k. Okay, and then you have this term, which, I mean, if you're familiar with Peter Janssen's work in 2003, it's just this singe function, which is sine of delta omega t over delta omega. Now, what is so this is a different shape of the kinetic equation, But what is clear from here is that, well, if we assume that gamma is 0, okay, gamma of k is 0, then G is 0, then you can simplify delta omega square by delta omega square, and you take the large box limit and you go back to the standard kinetic equation. Okay, so the good thing now is that if we set gamma equal to 0, you go directly back to the standard kinetic equation if you take the large time limit of this Sinch function. But just to understand, let me just to understand a little bit more, okay, the role of this extra term. Let me just again, this is the idea is not to have to study a particular model, but just to try to understand what would be the effect of having the dissipation on the same time scale as the nonlinearity. Let's assume, okay, that gamma of k, so this dissipation that usually is a function of k, is just a constant, so I call it gamma, okay? If I do that, then the kinetic equation reduces to this, form, which is again, resemble the standard collision integral, but apart from that, you have this extra term, which is here, which is delta omega sine delta omega t, delta omega squared, plus this damping term that you have here, okay? So let's check what are the differences between, let's say, the case in which gamma is equal to 0, okay? Which is this case. So if gamma is equal to 0, this just goes to the sine delta omega t over delta omega, and the function, the full function, which is right here, okay? So what you see here on the left is this Sinch function for different times, okay, at different time. And you see that for large time is the blue. So sorry, for short time is the blue, and then you have oscillation. And for large time, this function becomes narrower and narrower. And if you take the time t going to infinite, then you get a Dirac delta function, which is the standard wave kinetic equation. So, but what happens if you then don't include damping on this? And this is the result that you get. So I have made here a plot with epsilon equals 0.1, gamma equal to 5, but those are just arbitrary numbers that you can put. I mean, you can study for different numbers. And what you get here is that the interesting thing is that you have this oscillating function, but there is a peculiarity of this is that on the resonant manifold, and this is one of the results of which I'm presenting, on the resonant manifolds, this function is identically 0. Okay, so whenever you have exact resonances, okay, any small amount of dissipation would give a contribution that is equal to 0. Okay. So this means that resonances somehow lose, at least at short time. For longer time, maybe they can become, I mean, this function become narrower around 0, but for short time, clearly, exact resonances do not play a major role in this dynamics, in the dynamics with damping. Okay, so just an outline of the, I mean, this is a formal derivation that we make in the sense that we don't do a rigorous derivation in the sense that we do not control the reminders and we don't prove convergence or anything, but this is just a formal derivation. So basically what we do, the first thing that we do, we introduce a variable bk. So in order to, we remove this term, okay? So by just this transformation, from variable ak, we go to variable bk, and we rewrite the equation by renormalizing the dispersion relation. So we renormalize this omega, capital omega is just the dispersion relation which is renormalized, including the frequency shift, the nonlinear frequency shift, okay? And this sum excludes trivial resonances. Okay, then what you do, I mean, this is the way I did it. You can probably do it in a different way, but we can introduce angle action variables. So you have an equation for the action and an equation for the angles, which are written here. So far, no hypotheses have been made. So it's just no hypothesis. But then what we do, we expand in power epsilon the action and the angles. Okay. So ik is going to be equal ik0 plus epsilon ik1 and so on and so forth. We plug this into the equation, and we solve at each order, okay? And the result is that, okay, then we assume we solve at each order, assuming that at time t equals 0, the phases are randomly distributed in the interval 0 to pi, and the actions are identically independently distributed random variables. The expansion is carried out up to epsilon square order, and then we average over the initial phases. And if you average over the initial phases, the only contribution that we get is the only order epsilon square. And then we do average over initial actions, and then we take the large box length. So this is basically the procedure that you do in order to derive this equation. Okay, so I know that time is running, so but just sorry about that. Okay, so just this is just preliminary numerical experiment to see if things make sense in our model. So for simplicity, we assume like a narrow band approximation. So t is a constant, and omega k, the dispersion relation is k squared. For those who are familiar, this is the framework of the nonlinear Schrödinger equation, and we take gamma of kappa equal to a constant, which is gamma. Okay, we prescribe some. So we solve the deterministic equation and perform an ensemble simulation. So with different set of this is not if, but different sets of random phases. Okay, so we prescribe some spectrum, some whatever. I mean, this is a Gaussian shape spectrum, but you can play with any other spectrum. And then we solve also the associated wave kinetic equation with the one that you have seen, including dissipation. And here you see should see the answer, okay, for some parameters. So we have this initial condition is going to be the black line. This dissipation means just without nonlinear terms. So you remove from the kinetic equation the nonlinear term, and you just look at the dissipation. This is the dissipative, well, nonlinear Schrödinger equation, and this dissipative wave kinetic equation in red. So you see, I mean, the right away you have the nonlinearity is bringing up these tails. I mean, it's very quick. This happens at very. I mean, the movie doesn't show that, but and then we have that the damping is also acting, and on the light blue you see the ensemble simulations, and sorry, I don't know why you see this ensemble simulations, and in red you see the numerical simulation of the kinetic equation. And as you can see, I mean, for the number of simulations that we have done, which are more or less in the parameters we are considering, the result that we get are okay, reasonable. I don't know why I get this, but this is okay. So this should be the conclusion. Let me see why I'm getting these problems. But in any case, I think you have understood what I have done. So let me. Okay, so let me just, wrap up. I mean, it's 22 minutes already. So, okay, so we formally have derived the wave kinetic equation in the presence of dissipation term, which is act on the same time scale as the nonlinearity in the Zakharov equation. And we have highlighted the role of resonances in the presence of dissipation, or the fact that those resonances do not seem to play a major role. And then we have, I've shown you some preliminary numerical results, which are somehow support the theory that we have developed. So this is all in progress. So thanks a lot, and I'm ready for any question from you.
Thanks, Miguel. Perfect in time. So there is yes, enough time for a few questions. If any from the audience, please jump in. Anyone has to unmute if you want to make a question.
Here.
Oh. Yeah.
So it wasn't clear to me, but in the simulations that you're showing, the nonlinearity and the dissipation are of the same order, correct?
Well, this is it's hard. Yeah, this is what we try to do. Somehow they should be on the same order. It's hard to, yeah. I mean, the point is that it's hard to have them to be all the same order in all wave numbers. You see, because you have a spectrum. So, but this is more or less the idea.
Okay, thank you.
Hey, Miguel, can you hear me?
Yes, who's speaking?
Hello?
Hello?
Miguel?
Yes. Yeah. I can hear you.
Can you hear me?
Yes, I can.
Hello?
Hello?
Francesco, very, very nice talk. I would like to ask you, can you hear me now?
Your voice.
Can you hear me?
Yes, yes. Hi, Francesco. Sorry, I didn't recognize your voice. Hello. Yes, I can.
Is it better now?
Fine. Yes.
Okay. So Miguel, I want to ask you the quasi-resonant interactions. They show up in your formula when you do the dissipation, when you account for the dissipation. So, but you know, I mean, you did the formal derivation like in Janssen, so you will also account it for the quasi-resonance. Or they go away. No, they don't go away. When you put gamma equals 0, you basically get the extended kinetic equation. So the other things is what about, because I have done this work in 2014 for dekurtosis. I basically, to account for dissipation, I assume that the frequencies are complex. I assume that omega is equal to omega 0 plus I delta omega. And it may be possible that, you know, maybe doing that, you know, you provide a more direct derivation, still using a multiple scale, because I got similar results as yours. I didn't publish it at that time, but, you know, that's a classical approach, you know, so the frequency become complex. And so, and because they are of the same order, so I you know, I wonder if it should give similar. So what do you think?
Yeah. Okay. Thanks, Francesco. Okay. So first of all, yes. I mean, this is the same. I mean, if you set gamma equal to 0, you get to the result by Janssen. That's for sure. But if you have
with the quasi-resonant, quasi-resonant interaction.
There is an important thing. There is an important difference if you have gamma different from 0. Is the fact that for gamma equal to 0, when you have resonances, you have a peak in this function. Okay. In the case in which you have a damping, you have a 0. So exactly in the resonant manifold, the integral is 0. You see, so there is a main difference between these two results. Then if you take probably the limit properly of epsilon going to 0, then this could become a delta function as well. But there is somebody who's
okay.
But in any case, this is the main difference. And then concerning your other question, this is exactly what, I mean, if you look at this Zaharoff equation with damping, you can, I mean, call gamma 1 as an imaginary part of omega, right? So
yes.
It's the same thing. So, but it's not order 1. I mean, if you do it that way, that's what. Yeah. Okay. So if you get similar result, that would be, I mean, it's nice to.
It should be epsilon square.
If you have epsilon square, you get the standard wave kinetic equation. If you have epsilon square here, you get the standard wave kinetic equation plus this extra term of damping, okay, which is standard wave action balance equation. Yeah. So if it is epsilon square, but if it is epsilon, then you get this extra term, which are here. Okay.
Okay. Thank you.
Thank you, Francesco.
Hello.
Yes.
Hello, Miguel. Can I ask a question?
Yes, Peter.
Oh, the simulation you showed, was it in 1 dimension or 2 dimensions?
It's 1D. So it's
but you don't have resonant interactions.
Exactly. So in the simulation, which are 1D, we avoid all the problem with resonances because there are no resonances in 1D LLS. So so it's of course this is just the starting point, and one should do use models which have resonances and check the effect. But this is so far what we have done, which is the simplest thing that you can do. I mean, you have done that as well, right? So
yeah. Okay, thank you.
Maybe 20 years ago you have done that.
Yeah.
Okay.
There is time. One more question, if any, from the audience.
Miguel, I'd like to say a couple of words. First, it's very nice work, and this is potentially a very important result about the disappearance of peak because of the dissipation. So I was playing with the problem of complex omega, so it's in a similar way, but I didn't focus on the dissipation. I considered both dissipation and generation. And the problem I encountered was that, and I was deriving the generalized equation, so that's and a kinetic equation, and the problem I encountered was that everything was blowing up if you take into account generation, allow for generation.
Okay. I mean, this term is you can see this term as a generation as well, right? Because this uses
it should be the same. Yeah,
it should be the same. So it should be exactly the same. It's just change the sign. So the approach doesn't change at all. It's the same. You mentioned you said that everything was blowing up, but was that in numerics or in
analytically?
Analytically. So also we encounter secular growths, but we were able to deal with those secular growth by doing this transformation first, and by also removing by renormalizing the frequency, because if you renormalize frequency, you can avoid secular growth of the expansion. This is I mean, a standard way of
this is the standard thing, but
and we didn't. If you do it this way, you do not. I mean, you don't. I mean, we didn't encounter secular terms in the expansion.
Okay, thank you.
Thank you, Victor.
Thank you, Miguel.
Okay.
So if you don't mind, we move to the next speaker. So
yes, I just thanks to all of you. Thank you.
Please, Sergei, take the screen.
Okay, I'll try. And yeah, share. Okay, is it okay now?
Yes, it is okay.
Yes, so, and you can hear me and all that. So I'll try to speak then. Well, so basically, this is something that is quite close, well, in some sense related to what Miguel was talking about, except that I was basically trying to go beyond the kinetic equation. That is to look at it from outside, because we don't actually have much chance to do it. So this is this work is in collaboration with Victor, and there is some well, it's based on some measurements which actually in this talk almost will not be used, but still I mentioned that, and it's uses the Hasselmann equation code provided by Gerbrand. So what it is about. Let me see whether I can. Yes. So, first of all, we all sit on a very powerful theory, which is wave turbulence. That is, this is the turbulence of dispersive wave trains with weak nonlinearity. And first of all, this is a very solid, founded theory. That is, we have that linear behavioral system, that is waves coming unrelated from different directions. This actually brings the system close to Gaussianity. And then weak non-Gaussianity is regenerated by weak nonlinear interactions, which causes evolution. This is basically the general framework of the theory. And the theory appears to be quite solid. That is, it's based on some mild assumptions, which are sometimes violated, usually in one dimension, but in principle, it's usually considered that in the open ocean, there is absolutely no doubt that the theory is solid. Then the main tool of the theory is the Hasselmann equation. And usually it's considered to be based on the same solid foundation. That is, there is that view that whenever you question the Hasselmann equation, you actually question the wave turbulence theory, because the two seem to be quite linked. So, and yes, there is a consensus that it does, the equation does capture the main features of wave field evolution. So let's now see what it gives us, the equation itself. So I took Gerbrand's code and just applied it to a simple evolution with zero initial condition. That rather strong wind. And what we get, we know what we get in this situation. We get the evolution which is perfectly self-similar. That is, we know the known laws of it. There is that shape function. The thing is that this shape function is exactly the same, regardless of the nonlinearity level, because the equation is homogeneous with respect to spectrum. That is, if we just rescale all nonlinearities, then everything gets rescaled by epsilon power 6, yeah, and that's it. Sometimes this is quoted as an advantage, like the theory is universal. However, let's look. Let's look at the solution from the observational perspective. Is the similarity observed? The self-similarity observed in nature? Actually, not quite. That is, we have young waves. That's on the left, you see John Schwab gamma 3.3, which have that peaked shape. However, even for young waves, the shape of the spectral front is quite different if we just believe in John Schwab. I quote Babayan and Solovyov here. They also remarked in that paper that John Schwab was somehow informed by Hasselmann's numerical experiments at the time. Well, what this means, I don't know. This, from my perspective, this is what I would call bias, to be honest. But okay, nonetheless, so we have that widely accepted picture of young waves. And at the same time, we have mature waves. That is Pearson-Mascovitz spectrum, which does not seem to be even close in shape to the solution of Hasselmann equation. And also, there is that one thing which always fascinated me. If you look at the solution, this is Badulin's old numerical simulation, but we have that spectral front, which is practically straight, nearly to the top. But this means that if we sit at the beginning of just at the bottom, and we observe the growth of a harmonic as the spectral front approaches, we see that the growth is basically the same. That is, okay, at the very bottom, it has to be exponential, yeah, because this is the solution of linearized equations. But what? Does it remain exponential there at the top? Because that's what the straight front means. And this is sort of weird because, well, we know that this is not how nonlinear systems behave in the first place. Yeah? Nonlinear systems behave basically like this. This is averaged over 10,000 realizations, discrete system of 3,000 harmonics, Zakharov equation solution. Well, we have that growth of that initially small harmonic. It is exponential, yes, for the first approximately 300 periods. Then it comes off, and then we enter a different regime. So that's basically that's what we would expect when the amplitude grows. Then it cannot be the same regime of growth, because that's not what nonlinearity brings us. There must be some qualitative change. So in an attempt to understand what's happening here, we first created the direct numerical simulation algorithm based on the Zakharov equation. And basically at that time, we were thinking about some things that proved to be wrong. That is, we were thinking about growth rate, which in the kinetic equation scales exactly as nonlinearity power 6, while the dynamical time scale would be nonlinearity power 4. And we were kind of curious how these things interact, how these things change, are linked. So at that time, we suspected that we might get faster dynamical scaling due to coherence. And that would put into question the very assumptions underlying the wave turbulence theory. We didn't find any coherence. That is, we did find a small one as expected, but we didn't find any large departures from non-Gaussianity. And actually, although we did find these growth rates, dynamical growth rates, epsilon power 4 in the DNS, but to our surprise, they were not faster. That's what you would expect, that epsilon power 4 is larger than epsilon power 6, but they're actually slower. But what we found is a different shape of the spectrum, much less peaked, which we didn't believe at first. We actually attributed it to some flaw in the DNS, to be honest. Yeah, and we also found a strong intermittency of the growth, which let's now actually, we considered it initially as an artifact. Let's now look at this DNS growth in detail. For that, it's better to do it without angle averaging. That is, let's just consider the situation for one angle, zero angle, and angles close to it. So what we see, the growth on the spectral front is actually quite interesting. It goes, first it's exponential, then it's nearly exponential, but some intermittency appears. Then it suddenly stops. That is, there is a break of regime. We have something like first peak and then a drop after it. And then we have that regime of slower growth, which is continues for some time, looks algebraic really. And then there is another peak and then the spectral slope. If we look at the growth rate, we see that the initial growth is quasi-deterministic. That is, basically everything grows at the same time, although intermittent. Then neighboring directions behave completely differently. So there is a lot of intermittency there, and then everything becomes, well, there is still some growth after the peak, but I would say that this depends on the break-in parameterization, which here we use only the minimal necessary, because we need to have some break-in parameterization. Here it will not work without it, but we're trying to keep it not quite invasive. Now, if you look at this picture and you think that this is completely crazy, that's something that is just hard to believe, what is going on here. Well, I thought that too, but then I looked at some, this is actually measurements from Romero and Melville experiment. If you look at these spectra, these are 3 consecutive spectra, also non-integrated at 0 angle. And you see that this picture is somehow supported by measurements. That is, you do not have that narrow, well-defined peak, which is so typical for Hasselmann equation. You have actually some area of the peak, which is much wider. And when you actually integrate it over angle, you will see that everything becomes sort of rather, well, less peaked than what Hasselmann equation predicts. So in an attempt to understand that further, we actually derived what we call the generalized kinetic equation. And this is very much based on Peter's equation. That's basically where we got the idea. So that's basically what Miguel also used, except that this equation does not assume anything about time scale of the spectral amplitude. So it is non-local in time. So we were hoping to understand something there. However, in fact, well, the large time limit of the generalized equation coincides with that of the kinetic equation. So what we were trying to understand, the fundamental question was why we see all these differences in spectral shape, but the spectral shape of the generalized equation is basically the same. However, like that, we at least created an algorithm which was simple, transparent, and parallel. So in principle, we could benefit from the current, progress in computational resources, which become more and more parallel, and now 1,000 processors are not beyond reach. So now, then the idea was, okay, so now we have self-similar solutions, both in the DNS and in the kinetic equation, and they have different shapes. How can we make the DNS solution approach the kinetic equation solution? So it turns out that in the DNS, we can actually regulate the amount of the density of wave interactions. That is, we can, in fact, we have a parameter which we can change, and we can have more or less nonlinear interactions and more or less non-Gaussianity. So when we tried that, we discovered that, in fact, if we really keep those interactions thin, if we just decrease the number of interactions so that there is evolution, it becomes slow. Then suddenly we realized that this may be the answer, because here you have that that is when you have not so many wave interactions, the wave field is much closer to Gaussianity, and then the evolution is slow, and the shape also changes, the shape of the self-similar solution. That is, this front straightens up and approaches the shape known from the kinetic equation. And when you increase, when we increase the number of interactions, then we get something that approaches Pearson-Mascowitz spectrum. That was basically the that kind of a breakthrough in understanding what actually is happening here. And then we started thinking about it in terms of effects of non-Gaussianity. So now, if we look back onto the Hasselmann equation, when we derive it from a chain of equations. So we have a spectrum in terms of fourth order cumulant, and equation for the fourth order cumulant in terms of 6th order correlators. And then, as usual, we neglect the sixth order cumulant, and then the correlators, the sixth order correlators, can be expressed in terms of lower order correlators, that is second order and fourth order ones. So far, this is exact, there is no approximation. But usually, what is happening, the sixth order correlator is expressed only in terms of second order ones. And then we get a pair of equations, which we can solve the second one, and then we can write down the generalized kinetic equation immediately. That is, we have the equation of spectrum in terms of the spectrum is non-local in time, but then we take the large time limit and recover the Hasselmann equation. The question is that we are neglecting here. Yes, we are neglecting a small term, but this small term is actually on the right-hand side of the evolution equation. This means that it may become important in some on some time scale, which basically, if we drop it all together, we assume that this time scale is infinite, which basically means that we assume that non-Gaussianity is infinitely small. Actually, I did not understand that before I saw Miguel's paper with the Mateis, when suddenly it became clear. They actually show explicitly that all that you need to derive the equation is the randomness of phases. So, and as a result of this simplification, we get an equation which is in fact degenerate. It's homogeneous with respect to spectrum. And this means that the form of the solution loses any dependence on the level of nonlinearity. But this is in line with the central paradigm of wave turbulence theory. That is, if we do not account for finite non-Gaussianity, we cannot account for finite nonlinearity either. In this case, what if we do not drop this term? In this case, we cannot get a single kinetic equation. We have a system of two equations. One is for spectra, another one is for correlators, and obviously it operates in a space of over many more dimensions, roughly square dimensions. So we see that picture from that pair of equations. When harmonics interact in quartets, correlators also interact directly, and they interact in triplets. That is, this is the triplet of correlators. So it has three coefficients. You have three different interaction coefficients, because in fact, what is happening, if you have linked quartets linked through a plus pair or through a minus pair, the correlators actually feel each other. This is how finite non-Gaussianity works. And this system of equations is actually exact within the assumptions underlying the wave turbulence theory. Yes, strictly speaking, there is one more term we neglected, which is nonlinear correction to frequency, but probably it doesn't matter. But for the moment, it is just neglected. I think that so the crucial question is, this all should work on a certain time scale, because when you just start from zero, from cold start, as we call it, that is when your wave field is initially Gaussian. That's how you start the kinetics. Then it's so insignificant. The question is, what is the time scale when it becomes significant? It looks like it's quite small, about 100 wave periods, I would estimate it, but this is so far, well, that needs to be investigated further. Also, the important thing here is that actually the spectrum plays the role of coefficients in that interaction of correlators. So it looks like non-Gaussianity becomes more important around the spectral peak. And the thing is that, well, this term is always dropped, but it's always dropped not because there were any arguments ever in favor of dropping it. is because the problem is too complicated with it. So we drop it because, not because we have the right to drop it, but because we want to obtain a kinetic equation as a single equation. And this term is in our way. But that is last time at a talk at WISE, I actually was able to demonstrate within a discrete problem that this term indeed reduces growth rates whenever these growth rates are large, even for a modest levels of nonlinearity. That's basically what happens. In fact, now, so the work is in progress is to apply it to generalized kinetic equation, because the generalized kinetic equation has a transparent, perfectly parallel algorithm. And so this is a very convenient environment for applying this all. Okay, as far as I know, I'm speaking for 22 minutes. And probably this is where I should stop, at least, well, I can. That is because I think if there are questions, I would really be happy to answer that. That is, this is what, well, basically this is how the picture of exact kinetics should look here. I understand that this is quite refreshing. That is. Compared to the standard to standard kinetics. However, well, because now we have many more applications which involve not just integral characteristics of spectra, but also spectral shapes. It looks like that spectral shape, which is shown to us by the Hasselmann equation, is actually, well, simply incorrect. It is something that basically it's a picture for micro-nonlinearity world, just magnified. Because, well, if it's the same shape for all levels of nonlinearity, you're actually looking at infinitely small nonlinearity here. But nonlinearity 0.1 is not infinitely small, and that's typical steepness of waves in the ocean. So that is, I would say that from my perspective, this is actually what we see, the different spectral shape. And I just have to say that it seems that this has been a long-standing problem, the difference between wave modeling and observations. That is the inability of the kinetic equation to reproduce Pearson-Mascowitz spectrum, basically. And I think this is probably the answer to that. So that's basically what I wanted to say. I think, well, at least I probably should stop now.
Thank you, Sergei. So good timing. So there is, yes, time for a couple of questions. So it is already 6 p.m. in Europe. So the seminar is ending soon. Please present yourself if you want to make a question. Remember that you have to unmute if you have to make a question. No questions, so I make it one.
Okay, may I ask one question to myself?
Oh, but that was a question, but don't worry, go ahead.
Yeah, that is all I just wanted to say is that when you compare this DNS and Hasselmann equation, then there is that question. Okay, that's it may be that this front looks more realistic in DNS, but the slope doesn't look more realistic in DNS, because what we see is that we know very well that there is overshoot in spectra, and it is observed, it is measured. This is actually a feature of observations, and the DNS doesn't give it. The thing is that I think that this is another side of the same problem. That is, kinetic equation overestimates growth rates near the peak. This means that if something grows faster than it should, something else should decay faster than it should, because action is conserved. And actually, looking at what is happening with the generalized equation, these harmonics that are that they're close to the maximal growth, they actually interact the most with those harmonics behind the spectral peak. That's where downshift is observed. That is, I think it's not the same. Where that overshoot is goes down. I think it's not the same overshoot, basically. I think that in real oceanic waves, overshoot is primarily caused by breaking. And that shape, which appears to be similar in the Hasselmann equation, in fact, this is obviously caused by nonlinearity, but this is part of the same problem. That is, it's driven by the fact that we have too fast growth near the peak. That's basically what I'm thinking about it. Because that was the question which was asked already, and I wanted to answer it. So that's basically it.
Okay, online there is a question from Francesco Fedele in the chat. Is that because Francisco is not able to speak?
Yeah, now I see it.
Okay, can you read and
oh, yeah, but that's okay. Not that I fully understand what is here, to be honest. Well, but we know that phases become weakly correlated, yes, as a result of nonlinearity, because if phases are completely uncorrelated, then there is no evolution. How this is related to Brownian motion, I'm not sure I understand.
Francesco, are you able to explain or talk? Probably.
Well, but this is a simple picture. In fact, this is.
Can you hear me? Can you hear me?
Yes, Francesco.
No, I was trying to understand because usually phases are neglected when in the studies of the kinetic equation. Assume that you have a signal, you have your nonlinear signal eta of t. You do the Hilbert transform and you are able to get the phases, okay? So these phases will be a function of time. And what I notice is that they are not stochastically differentiable. They are like, they look like Brownian motion. Indeed, they are correlated. So they have, but they are jumpy. And I was trying to understand if this is an effect of nonlinearities that makes, phasors are nice and correlated, e to the I phi, it is fine, it's all good. But, if you look at this, the unwrapped phases, okay, that you can get from the Hilbert transform, any signal eta of t can be written down as an amplitude, as a function of time, e to the I phi of t. And so I'm talking about that phases.
I approximately understand what you mean, although, well, it's, but here we're dealing with turbulence. That is, the important thing is that we have a system of a lot of degrees of freedom. And we have phases that are by construction, they are nearly Gaussian. That is, we do not neglect them. We average over them because we have the right to do it because they are nearly Gaussian.
Okay.
What remains is that weak correlation, which actually allows slow evolution of a wave field. That's why the evolution is actually slow.
Actually, now, when you talk about correlation of phases, how do you measure it? What correlation of, how are you going to measure that correlation of phases?
It's actually a good question. It's not easy. That is in
It's not
principle,
easy, I know. Yeah.
In the DNS, I can do it directly, and I try to do it in many ways because, well, obviously one thing with what you can measure correlation of phases, that would be these higher moments, like kurtosis, for example, that gives you a good integral measure of correlation of phases. Yes, but it measures the real part of the correlator, and evolution is actually driven by the imaginary part, and it's much harder to measure because it's symmetric, there is no integral. So still, well, this is an open question how you measure it, to be honest.
Really?
Yeah, as far as I understand, because it's not, to me, the actual measure of correlation is your evolution, your downshift. That's what actually measures, because it's just directly linked to that. Or you can also measure that thing which is nonlinear part of the Hamiltonian. That's also what I was trying to do. This actually also tells you something. It's quite small. It's very small. It's like 4 orders smaller than the linear part.
Can I ask you something? This new extra term, the new term that you consider by evolving the 4th order correlator, would that correspond to the nonlinearities of the compact Zakharov equation? So, I mean, what is the effect of that term on the kurtosis? Will it tend to damp the kurtosis compared to the NLS? So, you know, what will be the...
Oh, this I don't know. That is, this I don't know. That's another open question. Well, kurtosis will, because we're considering a generic situation when basically kurtosis is small. Yeah, that is, I mean, that kurtosis which, because, well, okay, kurtosis has 2 components. Dynamical component, which is small. So there will be some effect on it, but it's not an interesting question because it will remain small anyway. And there is bound harmonics kurtosis, which is linked to the shape of the spectrum. So this shape of the spectrum changes it approximately by a factor of 2 or 3. That's basically my observation. But this is the difference of shapes between DNS and kinetic equation. But this is just, well, this is important, of course, but this is just a consequence of different shape, that's all.
Thank you.
Excuse me.
Yes.
Sergei, can I ask you a question?
You're very much welcome, Peter.
You know, on the one hand, we know from observations, say, from the 1970s already, that we have a considerable overshoot in the spectrum if you look at the spectral evolution as a function of fetch. On the other hand, you're saying that your DNS is not giving overshoot.
Yeah.
So my conclusion is that your DNS is not in order. However, if you do just the nonlinear interactions a la Hasselmann as implemented by Gerbrand, you see overshoot. So my conclusion is that your DNS is not kosher.
Okay, so I tried to answer this same question, but I must, because I expected you to ask it, but you didn't at first, and I asked it myself. That is a few minutes ago. But actually, what I mean is, let me, am I still sharing? I'm still sharing it, yeah?
Yeah, sure.
Okay, so I have that same slide, which I didn't show, mostly to save time. but also I just didn't want, I thought, well, okay, that's unnecessary. That is, yes, we have overshoot. It is well documented in measurements, and the DNS, no, it doesn't have it. And that's exactly what I was thinking for a long time, that DNS must be flawed.
Mm-hmm.
Yeah, but
yeah, for sure.
I was thinking it for years, to be honest. However, if you look at it from a different perspective, the overshoot is not always observed. It's observed for young waves, and then it goes down and almost disappears as waves mature. That's documented. That's documented by
you have no universality. You have no universality. Initially, for the young waves, you have overshoot, you have a sharp spectrum, and gradually spectrum will broaden and the overshoot will go down. And that's something you need to simulate, and you can't do that with your DNS.
I cannot do it, but the thing is that, well, okay, and what if we already talk about mature waves? Because for mature waves, we are more or less free of breaking near the spectral peak. Yeah, so actually the spectral shape of mature waves, it should be predominantly defined by nonlinearity. And then I can actually reverse your question. Then,
no, that's not true. The steepness is smaller, so the nonlinear effect becomes smaller.
Yes, but still, this is still the dominant effect which defines the shape.
No,
yes,
no, it's the wind input then, yeah?
For mature waves? Not really.
Yeah. You know, you have for instance, you have the wrong wind input in your DNS. You don't have a realistic wind input, so that, you know, you can't discuss it in your, it's not realistic what you're saying.
Well, look,
what kind of wind input are you using?
I don't depend on wind input. I can change it. It doesn't matter. It's that is, I tried many different formulations. I didn't try your wind input, to be honest, but I tried a few of them. It doesn't matter. The shape remains the same because this is. But what I'm trying to say here, that overshoot that is observed is primarily caused by breaking. That's what I'm thinking, and that's why.
Think, but well, that's not what I think, and lots of other people. You know, it's clearly, if you look at the shape of the rate of change of the spectrum due to nonlinear interactions, you clearly see that it is sharpening the peak and giving overshoot.
Let's look at Pearson-Mascovitch spectrum, which is well documented in observations. There is no overshoot there. Why then? Can you answer this question?
Because nonlinearity is much less. The steepness is much smaller.
But we in the...
So then you can see that from the kinetic equation, you know, it goes with a cube. So that's why for old Wincy, you will have much less impact of the nonlinear interactions. You get a broader spectrum.
But that's my point, because the kinetic equation has always the same shape of the spectrum. What you are saying effectively is that...
No, that's not true. In your equation has, but you don't have the right input and you don't have dissipation.
I do have dissipation, but...
yeah, and the tail, but not near the peak.
Well, it depends on the stage.
In your case, you will not deviate from the universal evolution, but you should deviate in order to get agreement with your observations.
I think this deviation is caused by breaking primarily. That's basically my current view. And yeah, it can be challenged, but I think there are strong arguments in favor of this. That is, the true form, which is caused by nonlinearity, is actually Pearson-Mascovitch. Everything that is different from it is caused by not nonlinearity, but something else. And that true shape is revealed for mature waves because all other factors fade out, including breaking. That's basically what I think about it. I know your point of view is different, but well, okay, let's then discuss when we can, but this is, that's important, I think. Yeah. So, but I was thinking about your words actually for a long time, but I think that well, I still think that the real spectral overshoot is due to wave breaking rather than nonlinearity. That's basically.
Yeah, but that's just a thought. The thing is, you mentioned that your DNS results are very sensitive to the parameter lambda, which is controlling the amount of interactions you have.
Yes.
And that might give, to me, that gives a clue that your results are flawed.
Yes, but that sensitivity is for small lambda. When lambda is well, not so small, then there is saturation. That is eventually the algorithm. Of course, I have checked that the algorithm structure is stable with respect to change of parameters. Yeah, there may be small change, but no, this is not. That was the first question I was asking myself. Of course, I'm actually, yes, that's the next correct question. But of course I made sure that there is a wide range of parameters where everything is stable. So yeah, that's it.
Hey, Sergei, Peter, if you don't mind, I would take.
Thank you. Thank you.
Thank you. Thank you, Peter. Actually, that's a very interesting discussion. Thank you.
Yes, very interesting for the two speakers, and the question were right to the point of the two presentations. So I think I'm going to conclude this seminar. So the next one will be in 1 month from now. And thanks the speakers, the audience, and see you next time. Have a good day or good evening, whenever you are. Bye.
Okay, thank you.
Thank you. Bye-bye.
Bye-bye.